So in today's video, we're going to be discussing VSEPR theory, which stands for valence shell electron pair repulsion theory, which allows us to predict molecular structure based off the number of bonds and lone pairs in a molecule. So we're going to be looking at various examples, and we'll be discussing topics such as electron domain geometry, molecular structure, hybridization, polarity, and bond angle. So for electron domain geometry, that is looking at the chemical structure and looking at all the electrons in the structure. And then we have subsets of the electron domain geometry, which are called molecular structures, and we can determine the molecular structure by looking at the number of lone pairs. So a fundamental assumption of VSEPR theory is that we want to try to minimize repulsions. So the list of greatest to least repulsions is our lone pairs, triple bonds, double bonds, single bonds. So we have a lone pair of electrons in a molecule that will cause the greatest repulsion, which will minimize the bond angles, we'll change the bond angles around the central atom. So next we'll talk about hybridization. Electrons of atoms are located in orbitals, which have different shapes and they have different energies. When these atoms are in molecules, they will undergo hybridization, which means the orbitals will combine to form new hybrid orbitals. And these hybrid orbitals will all have the same shape, but the shape will be different as the original orbitals. And they'll also all have the same energy, but this energy will be different than the energy of the original orbitals. So polarity can be determined by looking at the electronegativities of the various atoms within a molecule. For example, with carbon dioxide is a linear structure. So we have carbon and oxygen on one side and oxygen on the other side. The oxygens are more electronegative than the carbon, so they are each pulling outwards, and they will cancel each other out, giving it a net zero polarity. The first thing we'll talk about is acetylene, which is two carbons and two hydrogen. Carbons are the green, hydrogens are the red. The two carbons are formed via triple bonds, and the carbons are connected to hydrogen via single bonds. We will see that when we draw out the Lewis structure. There are no lone pairs in this. Because there are no lone pairs, the electron domain geometry and the molecular structure will be the same, which is linear. And because it's linear, the bond angle will be 180 degrees. It'll be a sp hybridization, and because it's a symmetrical molecule, it'll be nonpolar. So the next molecule that we'll discuss is boron trifluoride. When we draw out the Lewis structure, we'll see that it has 3 single bonds and 0 lone pairs. Because there are 0 lone pairs, we know that the electron domain geometry and the molecular structure are going to be the same, which is trigonal planar. And we can always tell the hybridization based on the electron domain geometry. So we know that this is a sp2 hybridization. The bond angles are 120 degrees, and this will be nonpolar because it's a symmetrical structure. Next is nitrite. Nitrite, after we draw a Lewis structure, we'll see that it has 2 bonding areas and 1 non-bonding lone pair. The bonding areas are a double bond and a single bond. The electron domain geometry will be trigonal planar because there are 3 electron densities, and the molecular structure will be bent because there is 1 lone pair. It'll be a sp2 hybridization, and the lone pair will affect the bond angles by making it less than 120 degrees, because as we discussed earlier, lone pairs provide more repulsion than other bonds, and it'll be polar due to it being a bent geometry and having that lone pair. Next will be phosphate, which is 1 phosphorus and 4 oxygens. We draw the Lewis structure, we'll see that there are 3 single bonds and 1 double bond between the phosphorus and the oxygens. Because there are 0 lone pairs, we know the electron domain geometry and the molecular structure will be the same, which is tetrahedral, and that tells us that this is an sp3 hybridization with bond angles at 109 degrees. The double bond will affect the bond angles very slightly, causing larger angles around the double bond and lower angles around the single bonds. It will be nonpolar due to the symmetrical shape of the structure. So next we're doing phosphorus trichloride. We look at the molecular structure. We'll see that it has 3 single bonds and 1 non-bonding area. So for this, we'll have the 3 chlorines and the 1 lone pair of electron up here. This is a tetrahedral shape for the electron domain geometry, and the molecular structure will be trigonal pyramidal. We know this will be sp3 based on the electron domain geometry, so the angles will be less than 109 degrees, and they are less than that because we have the lone pair, which is going to cause that repulsion pushing down, which will cause it to deviate from the idealized angles. And this will be a polar molecule because the chlorine is more electronegative than phosphorus, and the structure is asymmetrical. And next we have nitrogen dioxide, which when we look at the Lewis structure, we'll see that this has a nitrogen double bonded to 1 oxygen and connected to another oxygen via single bond, and there's 1 individual electron on the nitrogen. So this will be a trigonal planar electron domain geometry, as we can see here, and then it'll be a bent molecular structure. So we have the lone pair kind of pushing down on the 2 oxygens. We know that this will be an sp2, and the bond angles will be less than 120 degrees because the lone pairs are pushing down on those oxygens. And this will be polar due to the bent structure and the electronegativity difference between the nitrogen and the oxygen. So next we have phosphorus pentachloride. So there's phosphorus down there, and then 5 chlorides around it, connected via single bonds. So there are no lone pairs on this, so the electron domain geometry and the molecular structure will be the same, which is trigonal bipyramidal. The hybridization will be sp3d. All trigonal bipyramidal structures will have an axial and an equatorial position. So the axial will be at 180 degrees, and the equatorial position will be 120 degrees from each other. So here to here we have 90 degrees, and then another 90 degrees, and then 120 around. This will be nonpolar because it's symmetrical. Okay. So next we have sulfur tetrafluoride. So the sulfur will be connected to 4 fluorides, the blue balloons, and then the sulfur will have 1 lone pair. So the electron domain geometry will be trigonal bipyramidal, which has bond angles of 90 degrees and then 120 degrees. However, because we have that lone pair, that's going to be pushing down on those atoms, causing the bond angles to be smaller than 120, 90 degrees. This will be a polar molecule. So next we have sulfur hexafluoride. So the sulfur will be connected to 6 fluorides. There will be 6 single bonds and 0 lone pairs. So the electron domain geometry and the molecular structure will be the same, which is octahedral. And based on that, we know that the hybridization will be sp3d2. It'll all have 90 degree angles, 90, 90, 90, 90, 90, 90. And then this will be nonpolar because of the symmetry of the structure. The last one is iodine pentachloride. So we have iodine connected to 5 chlorides, which are the purple balloons. It'll have 1 lone pair, which is represented by the green balloon. The electron domain geometry will be octahedral, and the molecular structure will be square pyramidal. This will have an sp3d2 hybridization. Typically with octahedral geometries, it'll be 90 degrees. However, because we have the lone pair providing that repulsion, it'll reduce all the angles below 90 degrees. And this will be a polar structure because of the asymmetry of the structure.